Welcome to the Deep Sleep Science channel. Tonight, we're gently exploring the quiet brilliance of ancient technologies and the many ways human beings learned to shape the world around them. Before you settle in fully, please take a soft moment to like, subscribe, or leave a comment, and then simply relax as we begin. One of the most astonishing objects from the ancient world is the Antikythera mechanism, a Greek device built to calculate and display astronomical events. It was made with interlocking gears that could model cycles in the sky with a level of mechanical sophistication that still feels remarkable today. Rather than being a simple tool, it was a machine that turned celestial patterns into motion you could see and follow. It reveals that ancient technology was sometimes far more intricate than people imagine. The surviving Antikythera mechanism was recovered from a shipwreck near the island of Antikythera. For a long time, it was just one mysterious object among other artifacts from the sea. But closer study revealed something extraordinary hidden inside its corroded remains. The fact that such a delicate and complex device survived at all is part of what makes it so captivating. It feels like a rare message from a lost chapter of engineering history. Current dating places the manufacture of the Antikythera mechanism around 100 BCE, give or take a few decades. That means this device was created more than 2,000 years ago, in a world without modern machine shops, electric tools, or industrial production. Even with those limitations, its makers produced a precision instrument capable of expressing astronomical knowledge through gears and ratios. Its age makes its sophistication feel even more striking. The Antikythera mechanism is often described as an ancient computer because it encoded astronomical relationships mechanically. Instead of using electronic circuits, it used gear trains, carefully arranged so that turning one part would produce meaningful movements elsewhere. In a very real sense, it processed information through physical motion. That idea alone makes it one of the most awe-inspiring technologies of antiquity. Qanats moved groundwater by gravity through gently sloping underground channels, instead of relying on constant lifting. This was an elegant solution for dry regions where water had to be protected and transported with great care. By placing much of the system below ground, ancient builders could guide water across long distances while reducing exposure to heat. It is a quiet kind of engineering, but no less impressive for being hidden. The Persian Qanat system supported settlement and agriculture in arid lands by transporting water over long distances without pumping. Entire communities could exist because these channels made reliable water access possible where the surface environment seemed harsh and limited. In this way, a carefully measured underground slope became the basis for food production, settlement, and continuity of life. It is a powerful example of how subtle design can transform a landscape. UNESCO describes Qanats as a technological ensemble that supported communities for centuries and sometimes millennia. That description is fitting because a Qanat was never just a tumble. It was part of a much larger system involving maintenance, water sharing, storage, and the shaping of daily life around a hidden flow. Their long survival shows that some ancient technologies were not brief experiments, but durable civil achievements. Qanats also shaped architecture and landscape because reservoirs, mills, irrigation works, and gardens often grew around them. Water did not simply arrive and disappear. It influenced where people built, what they planted, how they organized labor, and which spaces became green and livable. In this way, the technology extended beyond engineering and into the very character of a place. It quietly organized both nature and human settlement. Roman aqueducts carried water to distribution points using carefully graded channels over long distances. Their success depended on precision, because the slope had to be gentle enough to maintain flow without damaging the system. What appears from a distance to be monumental stonework was also a lesson in fine control and patient measurement. They turned gravity itself into an urban service. Between 312 BCE and 226 CE, Rome built 11 aqueducts that brought water from sources as far as 92 kilometers away. That distance helps explain the scale of Roman ambition and planning. These were not small local pipes, but regional systems that linked city life to distant springs and watersheds. The reach of the aqueducts shows how ancient infrastructure could operate across a surprisingly wide landscape. Roman baths on a huge scale were possible only because aqueducts delivered reliable water supplies to cities. Without that steady flow, the grand bath complexes that Romans are famous for would have been impossible to sustain. The baths depended on a hidden technological foundation of channels, distribution, storage, and plumbing. In that sense, the visible luxury rested on invisible engineering. Roman hydraulic cement was made by combining lime with volcanic ash that reacted in water and hardened into durable mortar and concrete. This was not a rough improvisation, but a material system with remarkable practical power. It allowed construction in wet conditions and made large, lasting structures more achievable. Ancient builders were, in effect, learning how to guide chemistry toward architecture. Roman concrete was useful for waterside and marine construction because hydraulic mixtures could set in wet conditions. That gave Roman engineers an unusual advantage in harbors, coastal works, and other demanding environments. Instead of treating water only as an obstacle, they learned to build materials that could endure in its presence. This is one of the reasons so many Roman structures remained influential for centuries. Petra's Nabatean water system made extensive settlement possible in an otherwise arid landscape. What seems at first glance like a dramatic stoned city was also a highly intelligent hydraulic environment. Water had to be captured, guided, stored, and protected with care in order for life there to flourish. The city's survival depended on engineering as much as on architecture. At Petra, engineering was not only about supply, but also about flood control. In desert regions, water can arrive not only as scarcity, but also as sudden destructive force. The Nabateans had to think about both extremes at once, designing systems that preserved valuable runoff while guarding buildings and public spaces from damage. This dual challenge makes Petra's technology especially impressive. The Marib Dam is one of the best-known examples of pre-Islamic South Arabian dam technology. It stands as evidence that ancient hydraulic ambition was not confined to the Mediterranean world. In a region where water control could define survival and prosperity, dam construction became a central technological achievement. The scale and reputation of Marib show how important such works were. Some ancient Saudi dams still retain water today, showing the durability of their design, even when their original agricultural setting has changed. This persistence is deeply revealing. It shows that ancient builders were not merely stacking stone for short-term use, but creating structures with long-lasting hydraulic logic. Even when their surrounding societies changed, the physical intelligence of the dams remained. Zhang Heng's seismoscope of 132 CE indicated that distant shaking had occurred, even though it did not record a full waveform. That alone made it remarkable, because it translated an invisible event into a visible sign. Long before modern earthquake instruments, it offered a way to know that the Earth had moved somewhere beyond immediate human senses. Detection itself became a form of knowledge. The seismoscope used a striking visual design with dragons and frogs to indicate direction. This means the instrument was not only functional, but also physically expressive. Ancient technology could present information through symbolic forms, turning motion into a dramatic and understandable display. It reminds us that scientific devices were sometimes made to be seen as well as used. Kailan is traditionally credited with developing a papermaking method around 105 CE, using bark, hemp waste, old rags, and fishnets. The beauty of this process lies in the transformation of ordinary discarded materials into something capable of carrying thought. Paper was light, flexible, and practical in ways that many earlier writing surfaces were not. A humble change in material opened immense new possibilities for administration and culture. Paper spread from China to Central Asia and then to Baghdad, before eventually reaching Europe on a large scale. That movement across regions makes paper one of the clearest examples of a technology reshaping entire civilizations through adoption and adaptation. As it spread, it changed the cost and accessibility of storing knowledge. A material innovation became a communication revolution. The control of fire was one of humanity's earliest foundational technologies because it provided heat, protection, and a way to transform food and materials. Fire was more than warmth in the dark. It was a tool for changing the properties of the world, softening, hardening, cooking, and reshaping things that would otherwise remain inaccessible. In that sense, fire was an early gateway to nearly every later material technology. Stone tools became true technologies when people deliberately shaped hard, fine-grained stones for specific cutting jobs. The key change was intention and specialization. A sharpened edge made for one purpose is very different from an ordinary broken stone picked up by chance. This marks an early step toward designing tools to fit tasks, which is one of the deepest patterns in the history of technology. Neolithic people expanded their material toolkit beyond stone by learning to use clay for pottery and brick. Clay offered a new kind of possibility because it could be shaped while soft and transformed by heat into something durable. That meant containers, storage, construction materials, and other practical forms became easier to produce in regular ways. A common earth became a reliable technology. Early weaving replaced many animal skins with woven fabrics, marking a major technological shift in clothing and household production. Woven cloth is the result of ordered repetition, with threads brought together according to structure rather than chance. This allowed humans to create flexible materials in controlled sizes and textures. Clothing and domestic life became more adaptable through this quiet mechanical skill. One of the great turning points in ancient technology was the discovery that metallic ores behaved differently in fire and could yield usable metal. That discovery changed what heat could do. Fire was no longer only for cooking or warmth, but also a means of unlocking hidden materials from stone. The path toward metallurgy began with noticing that the earth itself could be transformed. The wheel belongs to the cluster of major 4th millennium BCE innovations that also included the plough, sailboat, and writing. It is important to see it not as a lonely invention, but as part of a wider age of technological acceleration. Several systems for movement, agriculture, and information were emerging in roughly the same broad era. The wheel sits among other foundational changes that helped reorganize human life. The plough mattered because it multiplied human labor by letting soil be turned more deeply and more consistently than with simple digging tools. This made cultivation more efficient and opened the door to more regular large-scale farming. A small change in how the ground was worked had large consequences for food and settlement. It is a reminder that agricultural tools often shape civilization in quiet but decisive ways. The earliest looms were simple frames that held warp threads under tension, so weft threads could be passed through in an orderly way. That arrangement may sound modest, but it introduced a repeatable structure for producing fabric. Once tension and pattern were controlled, weaving became a true mechanical process rather than a loose handcraft alone. The loom is one of the oldest devices built around rhythm, sequence, and order. Ancient technologies often spread not as single inventions, but as clusters of methods involving materials, tools, and skilled labor. A tool by itself was rarely enough. People also needed knowledge of how to make it, maintain it, and use it within local conditions. This means technology spread not just as objects, but as living practices carried by communities. Cuneiform became the most widespread and historically significant writing system of the ancient Middle East. Its importance lies not only in its age, but in its long, practical use across different languages and purposes. Administration, memory, legal records, and literature could all pass through this script. It became one of the great information systems of the ancient world. The name cuneiform refers to the wedge-shaped marks pressed into damp clay. That form came from the physical interaction between stylus and surface. In other words, the appearance of the writing was shaped by the material process used to make it. Script and writing technology were deeply connected from the beginning. Clay tablets were practical because they were cheap, abundant, and durable once dried or baked. This made them excellent for record-keeping in societies that needed reliable storage of information. A message impressed into clay could outlast fragile organic materials by a great margin. Much of what we know about early writing survives because clay was such an effective medium. Writing systems were not only invented for literature, they also served archival, administrative, mnemonic, and communicative purposes. Writing helped store grain accounts, preserve agreements, manage institutions, and organize memory beyond the limits of speech alone. It was a technology for expanding what a society could reliably keep track of. Long before books became common, writing was already doing essential practical work. Alphabetic writing was a major analytic breakthrough because it reduced speech into a limited set of basic signs. That simplification made writing more flexible in representing new words and names. Instead of requiring a massive inventory of symbols, an alphabet worked through a smaller, reusable set. This was a profound technological shift in how language could be encoded. Papyrus was a core Egyptian technology because it turned a Nile marsh plant into a writing material: rope, baskets, boats, mats, and many other goods. Few materials show such wide usefulness. A single plant could become part of transport, daily household life, and written culture. Papyrus is a beautiful example of how closely ancient technology could be tied to a specific environment. Papyrus rolls helped make portable texts possible long before bound books became standard. Portability matters in the history of knowledge. It meant that words could travel, be stored more compactly, and be handled in new ways. The roll was not simply a different shape for text, but part of a broader change in how writing could move through the world. Ancient numerical notation was itself a technology because it allowed counting, accounting, surveying, and administration to scale up. Number signs may seem abstract, but they are tools for controlling complexity. Once quantities can be represented clearly and consistently, land, labor, goods, and taxes can be managed more effectively. Numerals made organized large-scale administration more possible. The shadoof is an ancient hand-operated water-lifting device built around a long pole, a bucket, and a counterweight. Its design is simple enough to understand at a glance, yet clever enough to reduce human effort substantially. By balancing weight against weight, it helped people move water for irrigation in a controlled rhythm. It is a beautiful example of practical mechanics. A noria is an undershot water wheel that raises water using pots or chambers attached around its rim. As the wheel turns, the river itself helps power the lifting process. This means flowing water becomes the energy source for moving more water upward. It is an elegant way of using a landscape's own motion to support agriculture. The Archimedes screw moves water upward through a rotating helical device, and remained useful for more than 2 millennia. Its endurance says a great deal about the strength of the design. When a single principle remains valuable across centuries, it usually means it solved a problem with unusual clarity. The screw is one of those rare, ancient ideas that still feels immediately intelligible. Ancient hydraulic engineering often depended more on careful slope and gravity than on high-powered machinery. This is one of the most important patterns in ancient technology. Builders often worked by guiding natural forces rather than overpowering them. A well-chosen gradient could do the work of many laborers once the system was in place. Ancient water technology frequently determined where settlements could survive and how large they could grow. Water shaped food supply, sanitation, household life, and urban scale. In many places, the real foundation of a city was not its walls or monuments, but its access to managed water. Hydraulic systems often decided what kind of civilization was possible. The Romans recognized the value of cement even when they also used carefully cut stone masonry. This shows that ancient builders were not trapped by a single tradition. They could appreciate the beauty and precision of stone while also adopting materials that offered new structural possibilities. Roman construction often balanced inherited craftsmanship with innovative material thinking. Roman builders inherited the arch from earlier Italic traditions, but developed it into a signature engineering form. They applied it broadly and confidently in bridges, aqueducts, vaults, and monumental spaces. The arch turned compressive forces into opportunity, allowing stone and concrete to span openings more effectively than simple beams. It became one of the visual languages of Roman engineering. Vaults are essentially extended arches, and domes are continuous series of arches turned around a center. This idea helps reveal how major architectural forms can grow from one structural principle. Once builders understood how an arch carried weight, they could extend that insight into larger enclosed spaces. A calm geometric logic lies beneath some of the grandest ancient buildings. The baths of Caracalla demonstrate how Roman engineering fused water supply, concrete structure, roads, decoration, and imperial funding into one project. These baths were not just buildings for washing. They were integrated systems that depended on multiple technologies working together in a coordinated way. They show how ancient engineering could operate at the level of whole complexes rather than isolated devices. Ancient Egyptian faience was made from quartz, alkaline salts, lime, and mineral colorants rather than from true clay-based pottery. This means it occupied a special place between ordinary ceramics and more luminous decorative materials. Its glowing blue-green surface gave common ingredients an almost jewel-like appearance. Ancient material technology could be both chemically subtle and visually radiant. Ancient construction technologies often advanced by combining humble materials in clever ways rather than by using rare substances. Again and again, ancient builders showed that insight could matter more than rarity. Clay, stone, lime, ash, timber, and sand became extraordinary when arranged with care. Many of the greatest ancient achievements were made not from magical materials, but from intelligent combinations. Monumental ancient architecture was usually the visible result of invisible technologies, such as surveying, lifting, mixing, grading, and organizing labor. The grand facade is only the surface. Beneath it lies a world of measurements, transport, planning, and repeated skilled actions. To understand ancient buildings fully is to see them as systems of coordination as much as objects of beauty. Egyptian boats commonly combined sails and oars, a practical response to Nile winds and narrow channel navigation. This combination gave ancient navigators flexibility. When wind conditions were favorable, sails helped when maneuvering or difficult currents demanded more control. Oars remained essential. Ancient transport often succeeded through such layered practical solutions. The lateen sail was a crucial improvement because it was the earliest major fore and aft sail. Compared with older square sails, it offered greater maneuverability and changed how vessels could handle wind. Small adjustments in sail form can produce major consequences in navigation. This is one reason sail technology mattered so deeply in maritime history. The trireme was built as a light, fast warship with a thin shell of planks stiffened by keel and ribs. Its design shows that speed can come from careful control of structure and weight. Ancient shipbuilders understood that a vessel meant for rapid movement should not simply be larger or heavier. Sometimes performance depended on disciplined lightness. Roman roads are famous, but measuring distance accurately also mattered, and the odometer addressed that need. The idea was not only to travel, but to know how far one had gone. This converts motion into information, which is a profound technological step. Measurement often matters just as much as movement itself. Transport technology in antiquity was usually a balance between speed, labor, cargo capacity, and the predictability of weather. No ancient system solved all problems at once. Every ship, road, sail, or cart involved trade-offs shaped by geography and purpose. Ancient transport was therefore an art of choosing workable balances rather than pursuing a single ideal. Agricultural technology changed dramatically when iron tools became available to ordinary farmers in ancient China. Iron edges endured longer and performed differently from tools made entirely of wood or stone. Even modest improvements in cutting and turning soil could change the efficiency of cultivation over wide areas. Sometimes broad agricultural change begins with a tougher edge. Chinampas were not floating farms, but stationary artificial islands built in freshwater lakes. Their importance lies in the fact that they created productive agricultural land, where nature had not simply provided it in ready-made form. Instead of only adapting crops to the environment, people adapted the environment itself. This is landscape engineering in a deeply practical form. Water lifting devices such as shadufs, norias, chain pumps, and screws all addressed the same challenge in different mechanical ways. That variety is revealing. Different cultures and places often faced similar needs, yet solved them through distinct arrangements of leverage, rotation, gravity, and flow. Ancient technology was not one path, but many intelligent paths through the same problem. Across the ancient world, urban success usually depended on unseen systems for water, food, counting, and maintenance. Monumental walls and temples may survive most visibly, but daily civilization rested on quieter foundations. The systems that fed people, carried waste, tracked goods, and moved water often mattered most of all. Ancient technology, in the end, was frequently strongest where it was least dramatic. One of the most revealing things about the water system at Petra is that the Nabateans carved channels to divert runoff away from important facades and built spaces. This means their engineering was not only about bringing water in, but also about protecting architecture from water when it arrived too suddenly. In a desert setting, a rare storm could be just as dangerous as a long dry spell. So the same civilization had to think carefully about scarcity and excess at the same time. That balance shows a mature understanding of landscape, flow, and risk. Ancient dams in Arabia show that water storage and flood management were major technological priorities in desert civilizations. In places where rainfall was limited and unpredictable, storing water could determine whether a community prospered or struggled. A dam was not simply a wall placed across a channel. It was a planned intervention in the landscape, designed to slow, hold, and guide water in useful ways. This kind of engineering turned temporary rainfall into a more dependable resource. The Sad al-Hassid Dam's preserve traces of original plasters, mortars, and water outlets, which gives us a rare look into the details of ancient hydraulic construction. These features matter because they show that builders were thinking about more than just piling up stone. They understood sealing, flow control, durability, and the need to release water in a managed way. The preserved materials also remind us that many ancient structures were carefully finished and engineered, not rough or improvised. Even practical works could involve precise craftsmanship. Ancient irrigation technology often combined earthworks, masonry, plastering, and careful flow control rather than relying on one single device. A successful system might include channels, storage areas, walls, gates, and surfaces treated to resist leakage. In other words, irrigation was usually a whole network of choices working together. This is important because it helps us see ancient engineering as systems thinking. The water only reached the field reliably when all those parts cooperated. In many ancient societies, water engineering was a communal technology that depended on shared maintenance as much as original invention. A canal or tunnel was only useful if people kept it clear, repaired its weak points, and managed access fairly. This means the social side of the technology was just as important as the physical structure. Even the best design could fail without routine care. Ancient hydraulic works were therefore both engineering achievements and social agreements. Hydraulic works were often among the most socially important technologies in the ancient world because they directly affected food, health, and urban life. Reliable water supported farming, drinking, sanitation, bathing, craft production, and daily comfort. When a society improved its water systems, it improved many parts of life at once. This is why water projects often became central to the identity and stability of a civilization. They quietly supported everything else. The word pozzolana comes from volcanic ash near Pozzuoli, whose minerals made Roman cement especially effective. This is a good reminder that local geology could become a technological advantage. Roman builders were not working with abstract chemistry in a modern sense, but they clearly recognized that some volcanic ash produced better results than ordinary material. When mixed with lime, it helped create a mortar that could harden strongly and endure. A place name eventually became the name for a class of useful building material. The circular arch allowed Roman bridges to span farther than simple stone beam bridges usually could. A beam tends to place strong stress on its center, while an arch redirects weight outward and downward into its supports. That structural difference changed what kinds of crossings were possible. Roman engineers used this principle to make bridges stronger, more durable, and better suited to heavy use. A curved form opened new possibilities for movement across rivers and valleys. Roman bridge building depended on strong piers and careful foundation work, especially where riverbeds were soft or unstable. The visible arches above the water were only part of the achievement. Builders first had to secure the structure below, often in difficult and wet conditions. Without reliable foundations, even a beautifully designed bridge would fail. This shows how ancient engineering success often depended on hidden work that the finished monument no longer reveals. Large masonry domes became technically significant when Roman builders scaled them beyond what earlier traditions had commonly achieved. A dome is not just visually impressive. It is also a structural challenge because weight must be carried in a balanced way around a wide enclosed space. Roman experimentation with concrete and vaulting helped them enlarge this form dramatically. What looks calm and unified from below is actually the result of careful control of mass and force. Brick-faced concrete let Roman architects hide structural bulk beneath marble, stucco, and mosaics. This means the elegant visual finish of many Roman buildings often covered a very practical inner structure. Concrete provided mass and strength, while decorative surfaces created the final appearance people saw. The combination allowed builders to separate structure from finish more flexibly than earlier traditions often could. It was a powerful way to join engineering efficiency with visual richness. Coffered vaults reduced weight while preserving the visual impression of immense and powerful architecture. By recessing sections of the ceiling in a patterned way, builders removed some material without losing structural effectiveness or beauty. This made the surface feel lighter both physically and visually. It also created rhythmic shadow and depth across the ceiling. So the design was doing structural work and aesthetic work at the same time. Roman public baths were technological systems as much as they were buildings, because they depended on plumbing, heat management, water supply, circulation, and large-scale planning. A bath complex had to bring water in, move people through spaces, manage temperature differences, and handle drainage. This required many parts to function together smoothly. The baths feel luxurious when we imagine them, but behind that comfort was a deeply organized infrastructure. They were large civic machines for daily life. Egyptians valued faience partly for its luminous blue-green glaze, which made ordinary ingredients resemble precious materials. The effect was more than decorative. The glowing surface gave objects a vivid, almost jewel-like presence that connected them with ideas of freshness, life, and brilliance. This is a lovely example of how ancient artisans could use chemistry and heat to transform common substances into something visually elevated. The technology changed not only the object's surface, but also its meaning. Faience objects included jewelry, ritual items, vessels, and sculpture, showing that glaze technology served both beauty and belief. It was used in personal adornment, daily objects, and sacred or symbolic contexts. That wide range tells us that a single material technology could cross many boundaries in ancient life. It was not locked into one social rule. Instead, it became part of art, identity, ritual, and craftsmanship all at once. In Egypt, faience was associated with rebirth and solar brilliance, which means material technology and spiritual symbolism were closely connected. The blue-green color suggested vitality, growth, and luminous life. So when ancient Egyptians made faience objects, they were often doing more than creating something attractive. They were also working with a material that carried emotional and religious associations. Technology in the ancient world was often rich with symbolism, not purely practical. Stone masonry could be erected without mortar, but cement greatly expanded what builders could do with permanence, speed, and scale. Carefully cut stone can be extremely strong, but it also demands great labor and precision in shaping every block. Cement and concrete allowed builders to create masses, cores, and forms that would have been slower or harder to achieve with stone alone. This did not replace stone entirely, but it changed the range of possibilities. New materials opened new architectural ambitions. Many early Nile boats carried a single square sail and one level of oarsmen, showing a mixed system of wind and human propulsion. This was a practical answer to river travel, where conditions were not always the same from one journey to another. A sail could help when the wind was favorable, but oars were still essential for control, maneuvering, and difficult moments. Ancient transport often relied on combining methods instead of depending on one. Flexibility was part of the design. When Egyptians ventured into the Mediterranean and Red Sea, rowing remained essential because early sailing techniques were still limited. Square sails were useful, but they did not give the same control that later sail forms would provide. For longer or more complex voyages, crews needed the dependable force of human rowing. This tells us that ancient seafaring was physically demanding and technologically transitional. Boats could move by wind, but not yet with complete independence from muscle power. Ancient square sails mainly worked best with wind from behind, which shaped how early travel routes were planned and timed. Sail technology does not exist in isolation. It affects when ships can depart, which directions are easier to travel, and how much risk a journey involves. A square sail was powerful in the right conditions, but less flexible in others. Because of that, ancient navigation had to pay close attention to season, direction, and local winds. The triangular lateen sail increased maneuverability compared with older square sail systems. This mattered because ships could handle wind from a wider range of angles and respond more effectively to changing conditions. Even a change in sail shape can reshape trade, travel, and maritime confidence over time. The lateen sail did not eliminate the challenges of sailing, but it gave navigators more options. Ancient improvements were often subtle in form, but large in consequence. Ancient trade ships were often guided by successive landfalls rather than by the kind of open ocean navigation associated with later eras. Mariners commonly moved from one recognizable coastal point to another, reducing uncertainty by staying connected to visible geography. This made practical sense in a world where instruments were limited and weather could quickly turn dangerous. Travel was shaped not only by the ship itself, but by how navigators related to coastlines and known stopping points. A trireme could likely reach speeds above 7 knots and perhaps around 9 under oars, which is impressive for a hand-powered ancient warship. That speed depended on the coordination of many rowers and the lightness of the vessel's design. It shows how performance can come from discipline, organization, and structural efficiency, rather than brute size alone. Ancient warships were engineered for motion, not comfort. Their speed was a technological and human achievement at the same time. Greek and Roman ship technology shows that speed sometimes came from minimizing weight rather than maximizing bulk. A faster vessel often required careful restraint in construction, keeping the hull light while maintaining enough strength for use. This is a very modern-sounding design idea, yet it was already present in ancient shipbuilding. It reminds us that engineers in the ancient world were already thinking in terms of performance trade-offs. More material was not always better. The Truvius odometer concept used wheel rotations and gears to convert travel into counted miles. This is a striking example of turning physical movement into numerical information. Instead of merely experiencing a journey, travelers could measure it in a more exact way. The machine acted like a translator between motion and counting. That makes it part of the long history of instruments that turn the world into data. In the Roman odometer, a cogwheel dropped a pebble after a fixed number of wheel turns, creating a physical record of distance traveled. This is an elegant solution because it linked repeated rotation to a visible and countable result. You did not need to watch the whole process constantly. The system left behind a trace of the journey in the form of accumulated pebbles. Ancient engineers were often very clever in using simple mechanical logic to solve abstract problems. Water transport often moved goods more economically than overland hauling in the ancient world. A river or sea route could carry heavier loads with less friction and often less labor than wagons and animals on land. This helped shape trade networks, city growth, and patterns of settlement. Where navigable water was available, it often became a natural highway. Ancient economies were deeply influenced by the simple fact that water could carry weight efficiently. Shipbuilding and rigging were conservative technologies, which means useful forms often persisted for long periods with only gradual refinement. This conservatism was not backwardness. It was often the result of experience proving that certain designs worked well enough under familiar conditions. Shipbuilders tended to improve dependable forms rather than reinvent them constantly. Ancient technologies often evolved through steady refinement rather than dramatic replacement. Ancient navigation technology included not just hulls and sails, but also seasonal knowledge of winds and waiting patterns. Mariners had to know when to travel, when to delay, and how weather cycles affected movement. This kind of environmental timing was itself a form of practical technology. Knowledge of wind regimes could be as important as any physical device aboard the ship. In the ancient world, navigation depended on information carried in memory and tradition as much as on wood and rope. Cotton was being used in India by 3000 BCE, making South Asia one of the earliest major centers of cotton textile technology. That is significant because cotton behaves differently from fibers like flax or wool and requires its own processing traditions. Early mastery of cotton meant people had learned how to grow, prepare, spin, and weave a plant fiber that would later become globally important. This deep history shows that textile technology was already highly developed in ancient India. Ancient Egypt relied heavily on flax, while India became especially important for cotton and China for silk. This pattern shows how textile technologies often grew around the strengths of local environments and available plants or animals. Different fibers encouraged different traditions of processing and cloth making. The ancient world was not using one universal fabric system. Instead, regions developed their own specialties, each shaped by ecology, labor, and craft knowledge. Food production technologies and textile technologies often developed together because both relied on seasonal planning, plant processing, labor coordination, and repeated manual skill. Farming gave people fibers as well as food, and turning those fibers into cloth required organized work after harvest. In that sense, the field and the loom were more connected than they might first appear. Ancient household economies often linked agriculture and textile production closely. Both were core technologies of daily life. Screw presses were used in the Roman world for tasks such as pressing clothes, wine, and olive oil. This shows how a single mechanical principle can serve many different needs. By converting rotational force into strong downward pressure, the screw press became a versatile tool for processing and compressing material. Ancient engineers understood that once a good mechanical idea existed, it could be adapted widely. The same geometry could support several industries. Wooden screws in ancient presses reveal that precision shaping in wood could be technologically sophisticated long before modern machine tools existed. To make a large wooden screw work well, artisans had to cut forms that meshed reliably and could endure repeated force. That required patience, accuracy, and material knowledge. The result was a machine component that looks simple in principle, but is demanding in execution. Ancient craftsmanship often reached high precision through hand skill. Press technology transformed harvests into storable commodities by extracting liquids from fruit and fiber. Grapes became wine, olives became oil, and wet or bulky raw material became something easier to preserve, transport, and trade. This means presses were part of the transition from agricultural growth to economic value. They helped convert perishable crops into longer-lasting goods. Ancient processing technology often mattered just as much as cultivation itself. Ancient agriculture depended not only on growing crops, but also on processing them efficiently after harvest. A field alone did not guarantee prosperity. People needed tools and techniques for storing, pressing, drying, grinding, and distributing what the land produced. Post-harvest technology shaped how much value could be preserved from seasonal labor. In many cases, this determined whether abundance lasted beyond the harvest season. The Chinese chain pump is linked to the wider availability of cast iron in ancient China. This matters because stronger and more durable materials can change what kinds of machines are practical. With better access to cast iron, mechanical parts could be made in ways that supported repeated use and wider adoption. Hydraulic technology was not separate from metallurgy. Progress in one field often strengthened progress in another. Castor plowshares in China demonstrate how metallurgy could directly increase agricultural productivity. A stronger plow edge could work soil more effectively, last longer, and reduce the frequency of replacement or repair. Even a relatively small improvement at the tool's cutting point could produce broad gains across many fields and many seasons. This is one of the clearest examples of material science affecting food production. Better metal could mean better harvests. The most successful agricultural technologies in antiquity were usually the ones that matched local water regimes. A technique that worked beautifully in a river valley might fail in a dry plateau, and a desert solution might make little sense in a marshy area. Ancient people understood this through experience, even if they did not express it in modern scientific language. Effective technology had to fit climate, soil, slope, and water availability. Good design meant good fit. Farming technologies often became enduring traditions because they were embedded in social organization and seasonal routine. People learned them from previous generations, coordinated labor around them, and built yearly rhythms around planting and harvesting. This gave agricultural tools and methods a stability that was both practical and cultural. A successful technique did not remain only because it existed. It remained because communities kept living through it together. Early iron smelting could not fully melt iron, so it often produced a spongy mass called bloom mixed with slag. This is an important detail because it shows that ancient metallurgy was not as straightforward as simply liquefying ore and pouring metal into shape. Iron had to be worked through a difficult intermediate stage. What came out of the furnace still needed considerable refinement before becoming useful. Ancient metalworkers had to be skilled in both heat and follow-up processing. Reheating and hammering bloom expelled much of the slag and produced more workable wrought iron. This process means that the first stage of smelting was only the beginning. Metal became useful through repeated cycles of heating and shaping, which gradually improved its quality. The smith was not merely forming an object, but continuing the purification of the material itself. Ancient metallurgy was a combination of extraction, correction, and craft. Ancient metallurgy depended as much on repeated working and refining as on the first smelt. The furnace began the transformation, but hammering, reheating, and shaping completed it. This is why metalworking was both a technical and a skilled manual art. Good results required judgment, patience, and practical experience at every stage. Ancient metal objects carried within them a long sequence of controlled changes. Wood steel was produced in ancient India by sealing iron with carbon-rich material in clay containers and heating it until the metal absorbed carbon and melted. This method shows a surprisingly advanced understanding of how to influence metal quality through controlled conditions. The process created steel known for high quality and later fame far beyond India itself. It was not accidental. It depended on deliberately creating the right environment for transformation. Wootz became famous because it could yield very fine, high-quality steel, associated later with Damascus blades. The reputation of the material spread because people recognized that it behaved differently from more ordinary iron or steel. Its qualities were admired in cutting tools and weapons, and its production became part of a larger story of long-distance technological influence. This reminds us that ancient material innovations could travel through trade and reputation across great distances. Damascus steel is known for both exceptional hardness and a distinctive watered appearance. What makes it especially memorable is that its performance and its visual pattern were both admired. In other words, utility and beauty came together in the same material. That combination often helped a technology become famous. People noticed not only what it did, but how extraordinary it looked. In some Damascus steel production, repeated folding and welding intertwined layers of steel into complex patterns. This method required labor, attention, and repeated heating and shaping. The visible surface pattern was not superficial decoration added afterward. It emerged from how the material was made. Ancient craftsmanship often left its process visible in the final object, which is part of why such metals remain so fascinating. The lost wax process creates metal shapes by building a mold around a wax model and then melting the wax away. This is a beautiful technique because it allows a temporary form to guide the creation of a permanent one. The wax disappears, but its shape survives in metal. That gives artists and metal workers a way to capture fine detail and complex form. It is one of the most elegant transformations in ancient craft technology. Bronze casting benefited from the fact that molten bronze reproduces mold detail well and then contracts slightly on cooling, which helps the finished piece come free. These practical material properties made bronze especially useful for casting intricate forms. Ancient artisans may not have described this in scientific terms, but they clearly understood the behavior through experience. Good casting depends on knowing how the material flows and how it changes as it cools. Coin blanks were often first made by casting molten alloy onto surfaces or into molds before being struck. This means coinage was not simply about stamping images onto metal. It also involved preparing metal pieces of workable size and shape beforehand. Standardized money required standardized preparation. Ancient minting was therefore a technological process of shaping, measuring, and striking in sequence. Early coin production shows that standardization is itself a technology, not merely a financial convenience. When societies create repeatable forms of value, they rely on controlled size, weight, and metal quality. That requires organized production and attention to consistency. The coin becomes a tiny engineered object as much as an economic one. Ancient states and communities depended on such regularity. Purple dye in antiquity came from marine mollusks and required processing small glands that contained the color-producing substance. This made the dye extremely labor-intensive and helped explain why it became associated with wealth and power. The color was not easy to obtain, and its production required specialized knowledge and persistence. Ancient dyeing could demand both biological observation and careful handling. Prestige often rested on difficult processes. Sunlight played a role in developing the purple-red color on textile material once the secretion was applied. This means the dyeing process did not end when the substance touched the cloth. Light itself became part of the transformation. Ancient craftspeople were not only using materials, but also directing natural forces such as heat, air, and sunlight toward desired results. It is another example of technology as careful cooperation with the environment. Ancient dye technology could be biologically complex, chemically demanding, and highly labor-intensive. The final color on a fabric might be the end result of many hidden steps involving raw materials, preparation, exposure, and timing. Because of that, dyed cloth often represented a great deal more work than the finished surface suggests. Ancient luxury frequently came from process rather than from glitter. A deep color could embody a long chain of effort. Colored glass was produced by adding metallic oxides, while the glass was molten. That means ancient craftspeople were changing the color of the material from within, not simply painting the surface afterward. Tiny additions of different substances could shift the appearance of the final glass dramatically, turning a transparent melt into rich blues, greens, reds, or other tones. This is a very delicate kind of control because the maker had to understand how small ingredients would behave in intense heat. It shows that ancient artisans were already practicing a form of careful chemical design. Alexandrian craftsmen in the Ptolemaic period perfected colored glass rods that could be fused and patterned into decorative sheets. This required making separate pieces of colored glass first, then arranging them in ways that would produce planned designs when reheated. It was not enough to know how to make glass. They also needed to understand how different glass elements would soften, join, and hold their pattern together. The result was a material that could look almost like a painting made from heat and minerals. It is a gentle reminder that ancient technology often became most impressive at the level of detail. After Syrians invented glassblowing in the 1st century BCE, mosaic-style glassware could be formed by reheating and reblowing decorated hot glass. This changed what was possible, because a vessel no longer had to be shaped only by carving, molding, or casting. A bubble of hot glass could be expanded, turned, and guided into form, while still carrying decorative patterns from earlier preparation. The object was shaped while alive with heat and movement. It is one of the most graceful examples of ancient control over a fluid material. Ancient materials technology often created prestige, not from rarity alone, but from the controlled transformation of common substances. Sand, ash, quartz, plant matter, lime, and metal ores could all become extraordinary when treated with heat, timing, and skilled hands. This matters because it changes how we think about luxury in the ancient world. Something precious was not always precious because it was found ready-made in nature. Often it became precious because human knowledge had altered it in a difficult and beautiful way. Sundials are the earliest type of timekeeping device, using the movement of a shadow through the day. At first, this may sound simple, but it represents a subtle form of measurement. A sundial turns light and shadow into a reliable, visible pattern that people can use to divide time. Instead of only feeling that the day is passing, a person can watch time take shape on a marked surface. That is a quiet but profound step in human observation. A sundial works because the sun's apparent motion changes the position of a shadow in a predictable way. The device does not make time, of course. It reveals time by cooperating with the geometry of light and Earth's rotation. As the day moves forward, the shadow shifts in an orderly manner that can be tracked and interpreted. This is part of what makes sundials so elegant. They do not force nature into measurement, but borrow nature's regularity and make it readable. Clepsydras measured time by the regulated inflow or outflow of water rather than sunlight. That made them especially useful when the sky was cloudy, when the sun was not visible, or when time needed to be measured indoors. Water moved in a steadier and more controllable way than a shifting shadow under some conditions. Ancient people recognized that different settings required different forms of timekeeping. A water clock was a way of turning slow, continuous flow into counted duration. Water clocks solved a basic limitation of sundials by allowing time measurement when the sun was not practical to observe. This is important because it shows ancient inventors paying attention to the weaknesses of older technologies and trying to overcome them. A sundial is beautifully simple, but it depends on daylight and weather. A clepsydra extends measurement into other times and places. In that way, ancient timekeeping became more flexible and less tied to a single environmental condition. Ancient astronomy achieved high predictive power earlier than many other sciences. The reason is that celestial motions, though complex, often repeat in ways that careful observers can track over long periods. By recording patterns in the sky, ancient astronomers learned to anticipate certain events and cycles with surprising accuracy. This gave astronomy a special place among early fields of knowledge. It was one of the first areas where repeated observation could lead to dependable prediction. The astrolabe was an early scientific instrument used for reckoning time and for observational astronomy. It helped people connect the visible sky to calculation and orientation. Rather than being a passive object, it was a working tool for understanding where celestial bodies were and what their positions meant. Ancient instruments like this show that observation was becoming increasingly structured. The sky could be studied through devices, not only watched with the naked eye. A planispheric astrolabe represented the celestial sphere on a flat surface, making positions in the sky easier to calculate and visualize. This is conceptually impressive because it means ancient designers found a way to flatten a three-dimensional heavenly system into a useful two-dimensional instrument. It is not a trivial transformation. The instrument works by carefully preserving relationships that matter for measurement while simplifying the shape of the sky into something manageable by hand. Maya calendrical technology combined a 260-day ritual cycle with a 365-day year. This means time was being tracked in more than one rhythm at once. One cycle served ceremonial and cultural purposes, while the other followed the solar year more closely. Holding two structured systems together required discipline, notation, and tradition. Ancient calendrical technology was therefore not only about counting days, but about coordinating different kinds of meaning in time. Together, those Maya cycles formed a 52-year calendar round of 18,980 days. This long repeating cycle shows how ancient timekeeping could operate across scales, from daily ritual to multi-decade pattern. A person could place events not only in a short sequence, but also within a larger turning system that repeated far less often. That kind of layered timekeeping gives a culture a more intricate way of organizing memory. The calendar becomes both a practical and a cultural framework. Maya inscriptions often recorded historical and astronomical information through calendrical notation. This means timekeeping was built directly into the written record. Dates were not just labels added to events after the fact. They were part of how history and sky observation were understood together. In this way, the calendar became a tool for preserving knowledge, linking celestial order with human events across generations. Mesoamerican calendar technology was shared across cultures rather than belonging to only one people. This reminds us that ancient innovation often spread through exchange, adaptation, and regional tradition. A system could be refined in one culture and used or reshaped in another. Technology does not always stay within fixed political borders. Calendrical knowledge, like other forms of knowledge, often moved through networks of contact and continuity. Ancient numerical and calendrical systems were technologies of memory, administration, and prediction. They help people remember obligations, record events, organize ritual, plan agricultural activity, and understand recurring patterns. Without such systems, many large-scale social activities become much harder to coordinate. Numbers and calendars may appear abstract, but they are practical tools for managing complexity. They are among the quiet foundations of civilization. The abacus probably began as a board or slab that could organize counting marks or positions physically. This is important because it shows that calculation did not need to begin as writing alone. People could think through quantity by arranging objects or markers in space. A counting surface makes numbers tactile and visible. It turns arithmetic into something the hands can help the mind perform. Even simple counting boards show how ancient calculation often relied on moving objects in space, not just writing numbers on a page. This makes counting feel more physical and immediate. Instead of carrying all the relationships mentally, the user places them outside the body in an ordered arrangement. That external structure reduces confusion and supports more reliable calculation. Ancient mathematics often worked through tools that guided attention step by step. Timekeeping technologies in antiquity often translated natural regularities into visible, countable change. A shadow moves. Water rises or falls. A marked surface receives that motion in a form that can be interpreted. This is one of the most beautiful recurring ideas in ancient science and technology. Nature provides the rhythm, and the device makes the rhythm legible. Ancient astronomy and timekeeping were deeply practical because they affected ritual, agriculture, governance, and navigation. Knowing when seasons changed, when ceremonies should occur, or how to orient oneself could have serious consequences. These were not abstract hobbies separated from life. They were tools for organizing society and surviving within larger natural cycles. In many ways, ancient observational science began as a form of practical necessity. Trepanning is one of the oldest known surgical procedures, involving the deliberate drilling or scraping of the skull. It is a startling example of how early medical intervention could become highly invasive. The fact that ancient people attempted such a delicate and risky act suggests both courage and accumulated practical knowledge. They were not always avoiding the body's hardest problems. Sometimes they confronted them directly with the tools they had. Evidence that trepanning goes back thousands of years, showing that surgery has very deep roots in human history. This long time span matters because it means medical experimentation did not begin recently in human terms. For a very long time, people have tried to intervene physically when illness or injury demanded it. Ancient medicine could be cautious, but it could also be bold. The body was already being treated as something that could be carefully acted upon. Ancient trepanning may have been used for ritual reasons, head injuries, or other medical aims. That uncertainty is itself revealing. It reminds us that ancient practices often sat at the boundary between medicine, belief, and observation. A single procedure might have had more than one meaning depending on time and place. Ancient medical technology did not always separate the practical from the symbolic as sharply as modern systems do. The Edwin Smith Papyrus from ancient Egypt recorded surgical techniques and placed emphasis on hygiene. This is a very important detail because it shows medicine moving towards structured description rather than relying only on oral tradition. A written medical document preserves cases, observations, and procedures in a way that can be studied and transmitted. The mention of hygiene also suggests attention to cleanliness as part of good treatment. Ancient medicine was more systematic than many people assume. Sushruta's medical tradition in ancient India described surgical instruments and techniques, including early reconstructive surgery. This tells us that surgery had become organized enough to require named tools and formal methods. Reconstructive procedures are especially impressive because they demand planning, delicacy, and awareness of healing. Ancient practitioners were not only removing or cutting. In some cases, they were trying to restore form and function carefully. Ancient surgery was already becoming systematic when texts began cataloging tools and procedures rather than preserving only scattered remedies. Once knowledge is organized into instruments, steps, and methods, it becomes more teachable and repeatable. That does not make it modern in every sense, but it does mark a major change. Surgery becomes a craft with structure. Ancient technical writing helped to make that possible. Galen stressed anatomy and helped lay foundations for experimental physiology in the Roman world. Anatomy matters because understanding structure changes how one interprets illness and function. By paying close attention to body parts and their roles, Galen contributed to a more organized way of thinking about the living body. His work was not perfect by modern standards, but it was influential because it treated the body as something that could be studied in a reasoned way. Galen recognized that arteries contain blood, correcting older ideas that treated them as air-filled. This is a fine example of observation overcoming inherited belief. Sometimes a long-accepted assumption remains in place until someone studies the body more carefully and notices a contradiction. Ancient science often advanced in these small but meaningful corrections. Better understanding could come from looking more closely at what was already there. Hippocratic medicine linked health to environment, diet, and lifestyle, showing an early systems approach to the body. Rather than seeing illness only as a sudden isolated event, This tradition considered the body in relation to climate, food, habits, and surroundings. That way of thinking remains familiar even now. It shows that ancient medicine could sometimes view health as a balance shaped by daily life. The body was understood within a wider context. Ancient Rome invested in public health technology through aqueducts and sewerage systems. This is significant because it means health was addressed not only at the bedside, but also through infrastructure. Clean water and waste removal changed disease risk and daily living conditions for entire populations. In this sense, public engineering was part of medicine. A city could become healthier because its hidden systems improved. Mohenjo-daro's many baths and washrooms suggest that sanitation and cleanliness were built into urban design. This is remarkable because it shows concern for washing and drainage at the level of ordinary domestic life. Hygiene was not treated only as a luxury for elites or priests. It was incorporated into the city's built form. Ancient planning could therefore express practical care for everyday bodily needs. Most houses at Mohenjo-daro had small bathrooms connected to drainage, which is astonishing for a Bronze Age city. It means private washing spaces and waste management were common enough to be worked into many homes. This points to an advanced understanding of how domestic comfort and sanitation could be structured through architecture. Ancient urban life in some places was more technically organized than older stereotypes suggest. Ancient health technology was often civic rather than purely medical, with drains, baths, and water systems doing preventive work long before modern public health language existed. This is an important perspective. A society does not improve health only by treating illness after it appears. It also improves health by shaping the environment in which people live. Ancient infrastructure sometimes performed exactly that quiet protective function. Cataract surgery by couching has ancient roots and was associated in historical tradition with India and possibly Egypt. That means delicate intervention in the eye, one of the most sensitive parts of the body, was attempted in antiquity. Even when methods were risky, the attempt itself shows a striking willingness to develop targeted treatment for specific conditions. Ancient medicine could be surprisingly focused in its procedures. The long history of cataract treatment shows that delicate eye procedures were attempted in antiquity despite obvious risks. Vision loss is such a serious problem that people were willing to try difficult interventions in hopes of improvement. This tells us something human as well as technical. Ancient practitioners were responding to real suffering with the best methods they believed could work. The history of surgery is also a history of persistent effort against limitation. Ancient medicine relied heavily on observation and accumulated practice because many treatments had to be judged by visible outcomes. Without modern laboratory testing, physicians and healers often worked by watching what happened carefully over time. Did a wound improve, worsen, or remain unchanged? Did a patient's symptoms shift after a procedure or remedy? Observation became the laboratory of the ancient world. Hygiene appears in ancient medical texts not as a modern addition, but as a long-standing practical concern. Cleanliness in wounds, bodies, and living spaces was noticed as important long before germs were understood in modern terms. Ancient people may not always have known why certain hygienic habits helped, but repeated experience taught that they often did. Technology sometimes begins with pattern recognition before theory catches up. Public bathing in some ancient cultures blended sanitation, social life, and engineering. A bath was not simply a place to get clean. It was part of a carefully managed environment involving heated rooms, flowing water, drainage, surfaces, and circulation. At the same time, it was also a place for gathering and daily routine. Ancient technology often worked most powerfully when it merged utility with social habit. Ancient medical technology included texts, instruments, habits, and infrastructure, not just drugs or surgery. That broader view helps us understand the field more accurately. A civilization's health practices could include scalpels and splints, but also drainage systems, bathing facilities, written case records, and hygienic routines. Medicine was not always confined to the healer's hands. Much of it was built into the environment. The history of ancient medicine shows that a city's drains and water channels could matter as much as a physician's skill. This may be one of the calmest and most important lessons in the subject. Individual treatment is valuable, but shared infrastructure shapes the health of thousands at once. Ancient societies that managed water and waste well created a quieter kind of healing in everyday life. Prevention can be one of the greatest technologies of all. Weaving technology dates back at least to the 5th millennium BCE in the form of early fixed-frame looms. That long history tells us how central cloth-making was to human life. A loom is not just a support for threads. It is a device that stabilizes a process, turning repeated hand motions into controlled structure. Ancient textile technology begins very early because clothing, storage, and domestic comfort all depended on it. Looms separated warp threads into 2 alternating sets, making the path for the weft repeatable and efficient. This separation may sound like a small detail, but it changes weaving completely. Once the threads are organized in a regular pattern, the movement of the weft becomes faster, cleaner, and more reliable. Ancient mechanical thinking often worked like this. A simple structural distinction could create a major gain in efficiency. Textile technology is one of the best examples of ancient mechanical logic because every woven cloth is built from repeated patterned motions. The loom does not act by force or violence. It acts through order, rhythm, tension, and sequence. The fabric grows from the calm repetition of a process that keeps yielding stable results. That makes weaving one of the most quietly mathematical crafts of the ancient world. China's silk tradition became famous enough that knowledge of silk working later traveled westward. Silk was admired not only because it was fine and beautiful, but because it depended on a demanding chain of expertise. Producing it required understanding delicate fibers, careful processing, and skilled weaving. When other regions wanted silk, they were not only seeking an object. They were encountering a powerful and specialized technological tradition. Persia became an important center of silk trade between East and West under the Parthians. This shows how a technology can travel through exchange even when production remains rooted elsewhere. Trade routes carry more than goods. They carry techniques, fashions, values, and pressure for imitation or adaptation. Silk's movement across regions helped connect distant societies through one refined material. Silk dyeing and weaving became developed crafts in Syria, Egypt, Greece, and Rome. As silk spread, different regions learned to work with it in their own ways. This is a common pattern in ancient technology. A material arrives from one tradition, and then new communities build fresh skills around it. In time, the imported material becomes part of local craft history too. In some Western regions, silk workers unraveled imported fabrics to recover usable yarn. This is a fascinating detail because it shows technical adaptation under conditions of limited supply. If raw silk was hard to obtain, artisans could still learn from and reuse finished imported textiles. Ancient craftspeople were often very resourceful in this way. They found ways to work within scarcity without abandoning the material entirely. Pre-Columbian peoples in both Peru and Mexico developed advanced weaving and dyeing before European arrival. This is a useful reminder that sophisticated textile technology was not limited to Eurasia or North Africa. Across the world, people were mastering fibers, patterns, and colors in highly skilled ways. Ancient technology had many centers. textile excellence emerged independently in more than one civilizational tradition. Peruvian fine fabrics were noted as comparable in some ways to those of ancient Egypt, despite no assumed contact between the two traditions. That comparison is striking because it shows how different societies can reach similarly high levels of technical achievement through separate paths. Fine weaving depends on patience, control, and long practice wherever it appears. Ancient textile mastery was not an isolated miracle. It was a recurring human accomplishment. Ancient textile technology was global, with different fibers dominating in different environments. Flax, cotton, silk, wool, and other materials each encouraged different methods and traditions. This means textile history is really a story of many parallel solutions shaped by ecology and craft. Ancient people did not all wear or make cloth in the same way. Variety was one of the field's defining strengths. The shuttle was a small but very important weaving tool because it carried the weft thread cleanly through the warp. Without it, the process would be slower, less smooth, and more tiring over long periods of work. The shuttle helped turn weaving into a more regular and efficient rhythm, allowing cloth to grow row by row with greater consistency. It is a good example of how ancient technology was often improved by modest tools rather than only by large machines. Sometimes a quiet object that fits in the hand can transform an entire craft. Reed styluses were used to impress cuneiform signs into damp clay rather than draw them with flowing lines. This shaped the writing itself because the tool naturally made wedge-like marks when pressed at different angles. In that sense, the physical form of the script came directly from the material and the instrument. Ancient writing was not only about language, but also about the contact between hand, tool, and surface. The look of cuneiform is really a trace of repeated motion in clay. Some important Mesopotamian texts extended across multiple clay tablets, showing that ancient record systems could already handle long and complex works. This means writing in that world was not limited to short labels or small transactions. A larger text could be divided into sections, preserved across several tablets, and organized in a meaningful sequence. That required planning, continuity, and methods of keeping the tablets related to one another. Even in very early information systems, long-form storage was already possible. The earliest known books include Mesopotamian clay tablets and Egyptian papyrus rolls from the early 3rd millennium BCE. That tells us that the idea of preserving extended written content is very old. A book in the ancient sense did not need to look like a bound modern volume. It could be a sequence of tablets or a roll of prepared writing material. The physical form changed, but the purpose remained familiar: to store and carry structured thought beyond the moment of speech. Once alphabets appeared, they made it easier to represent new words and proper names than many older writing systems did. This is because a small set of sound-based signs can be recombined very flexibly. Instead of needing a vast store of fixed symbols, writers could build words out of repeatable elements. That greatly increased adaptability, especially when languages changed, borrowed terms, or recorded unfamiliar names. A compact symbolic system opened the door to broader and more flexible expression. Ancient writing technology depended just as much on the writing surface as on the script itself. A symbol carved into stone behaves differently from one pressed into clay or brushed onto papyrus. The material affects speed, permanence, cost, portability, and even the style of writing. So when we think about ancient literacy, we should not imagine script flourishing free from matter. Writing was always a partnership between language and substance. Papyrus grew best in shallow fresh water or water-saturated ground, which tied its usefulness closely to the Nile landscape. This is one reason Egypt became so strongly associated with it. A local plant, supported by a particular river environment, could be transformed into one of the ancient world's most important writing materials. The geography of the Nile helped shape the technology of record-keeping. Sometimes an ecosystem quietly determines what kinds of information culture can flourish. In ancient Egypt, papyrus was not only practical but symbolic, and it was associated with freshness, flourishing, and Egypt. This means the material carried cultural meaning beyond its everyday use. A plant that became rope, writing sheets, and household objects also became part of visual and symbolic language. Ancient technologies were often surrounded by ideas and associations that gave them emotional weight. Utility and symbolism could live together in the same material. The Egyptian use of papyrus shows that a plant can become both a raw material and a national symbol at the same time. That is a gentle reminder that technology is not always separate from identity. When a civilization relies heavily on a particular resource, that resource can enter its art, imagery, and self-understanding. Papyrus was useful, but it also helped express a sense of place. The natural world, daily craft, and cultural meaning could become deeply intertwined. Fragile writing materials usually survive poorly, which is why clay and stone preserve a larger share of the earliest written record than papyrus does. This affects the history we can recover. What survives is not always what was most common, but often what endured best physically. Entire worlds of writing may have been lost simply because their materials decayed. Ancient technology therefore shapes not only what people recorded, but what later ages are able to remember. Roman numerals used a limited set of symbols such as I, V, X, L, C, D, and M to represent values. That small collection made the system recognizable and consistent across many uses. These symbols could be arranged to form larger numbers according to agreed patterns. The system feels very different from modern positional notation, yet it served practical functions in administration, inscriptions, and counting. Ancient numerical technology often relied on symbolic economy rather than mathematical compactness. Roman numerals were additive in many cases, so a symbol placed after another of equal or greater value added to the total. This means that number building often worked by accumulation. A reader had to interpret the sequence as a structured sum rather than as a set of place values like those used in modern decimal notation. Though this could become cumbersome for some calculations, it was still perfectly workable in many everyday contexts. Ancient numeral systems often reflect different priorities from the ones we are used to now. The Rhind papyrus is one of the chief sources for understanding ancient Egyptian numeral practice and arithmetic. It gives us a precious look into how mathematical thinking was written down and taught. Rather than leaving us only with monumental inscriptions, it preserves practical examples and procedures. That makes it valuable not just as an artifact, but as evidence of method. Ancient mathematics comes alive most clearly when a working document survives. The true cleverness of the shadoof lies in its counterweight, which helps raise a full bucket with less human effort. This is a very simple mechanical advantage, but it matters greatly in repeated daily work. Instead of lifting all the water entirely by strength, the user works with balance and leverage. The device turns a tiring task into something more manageable and rhythmic. It is a fine lesson in how ancient engineering often made labor lighter without making machines complicated. Shadoofs were used for irrigation and remained practical for centuries because they could be built and repaired locally. This durability came not only from the design, but from the fact that communities could make them from familiar materials. A technology lasts longer when people understand it, trust it, and can maintain it without outside dependence. That helps explain why the shadoof endured so well. Its elegance was partly social as well as mechanical. As a noria turns, the attached containers fill when submerged and empty into a trough once they rise high enough. This creates a repeated cycle in which water lifts itself by means of rotation powered by the river's motion. The system is calm, visible, and easy to understand once seen in action. It turns flow into elevation through a chain of repeated small events. Ancient machines often worked through this kind of steady, readable rhythm rather than sudden force. Some ancient norias could be as large as about 12 meters in diameter, showing that water-lifting devices could become truly monumental machines. A wheel of that scale is not a minor village tool. It is a large engineered presence in the landscape, joining practical function with visual impact. Its size reflects both the ambition of the builders and the seriousness of the water problem it was helping to solve. Ancient technology could be modest or grand, depending on need and setting. The Archimedes screw is a good example of an ancient idea surviving in modern pumping systems with only minor conceptual changes. That is one of the strongest compliments a technology can receive. If a principle remains useful across thousands of years, it usually means the design captured something fundamental and efficient. Materials and power sources may change, but the core geometry remains valuable. Some ancient solutions were so clear that later ages never had to abandon them. Vertical shafts in canat systems allowed excavation, ventilation, and maintenance along the underground channel route. These shafts were essential to both the construction and the continued life of the system. Workers needed access points to remove material during digging, to let air circulate, and to repair problems afterward. So the canat was not just one tunnel, but a network with periodic openings serving different roles. Ancient subterranean engineering depended on thoughtful access as much as on hidden flow. Carrez systems are regional variants of the same underground water technology found across arid and semi-arid regions, from western China to North Africa. This wide distribution shows how a basic hydraulic concept can travel and adapt across very different cultures and landscapes. Local names and construction details may change, but the underlying principle remains recognizable. Water is collected below ground and guided gently by slope. Ancient technology often spread by preserving the core idea while allowing local variation. Only part of a Roman aqueduct needed arches, and much of the system actually ran underground in stone or terracotta conduits. The arches are what people tend to remember because they are dramatic and visible. But the quieter reality is that many aqueduct sections were buried or enclosed, hidden from sight. This is a useful reminder, but the most iconic image of a technology is not always the whole technology. Much of ancient engineering did its best work invisibly. Roman bridges existed in wooden, pontoon, and stone forms, which reflects flexibility rather than a single standard solution. Builders adapted their methods to location, urgency, available materials, and the purpose of the crossing. A temporary bridge for military movement might differ greatly from a permanent civic structure. This variety shows that Roman engineering was not rigid. Ancient builders were often practical enough to choose the right type of bridge for the right circumstance. Ancient transport technologies were shaped by environment, because rivers, seas, deserts, and mountains each demanded different solutions. A design that worked well on open water might fail in narrow channels, and a road suitable for one terrain might become useless in another. Technology was always in dialogue with place. This helps explain why ancient transport systems show such variety across regions. The land and water themselves were part of the design process. The earliest known iron plough from northern Henan dates to the Warring States period. This gives us a clear point in time when iron agricultural tools were already present in a meaningful way in ancient China. Such finds matter because they turn general ideas about progress into concrete evidence. An excavated ploughshare allows us to say not only that iron farming tools existed, but that they existed in a specific place and period. Archaeology often anchors the history of technology in this very calm and precise way. That early Chinese iron ploughshare was a small V-shaped iron piece mounted on wooden elements. The detail is important because it shows how new materials were often introduced gradually, rather than replacing older ones completely. Iron did not appear all at once as an entire metal machine. Instead, a crucial working edge was improved, while the larger body of the tool remained parky wooden. Ancient technological change often happened through these mixed forms, where old and new materials cooperated. Even a modest iron plowshare represented a major gain in durability compared with all wood or stone tools. The edge of a plow does demanding work, meeting soil, roots, and repeated friction again and again. If that edge lasts longer and performs better, the whole agricultural process benefits. Small material improvements at the point of contact can have large practical effects. Ancient tool-making often advanced exactly in this quiet, focused way. Chinampas were typically long, narrow plots built from layers of vegetation, dirt, and mud. This layered construction created fertile and manageable growing spaces within shallow lake environments. The shape of the plots also helped with access, irrigation, and maintenance. Rather than being random piles of earth, chinampas were carefully formed agricultural surfaces. They show how ancient farming could begin with deliberate land building as much as with planting. Chinampas show that agricultural technology can mean creating new land rather than merely improving existing soil. This is a striking idea because it expands what farming can be. Instead of simply choosing a good field, people actively engineered productive ground where there had been water and marsh. That changes our picture of agriculture from cultivation alone to environmental design. Ancient food production could involve reshaping whole settings, not just tending crops. Ancient bronze work was often cast rather than heavily hammered because bronze is comparatively brittle. This material behavior affected the whole craft tradition built around it. A metal that does not respond kindly to repeated heavy hammering invites different methods of shaping. Casting allows the desired form to be created while the metal is molten, avoiding some of the limitations of mechanical working afterward. Ancient artisans were always adapting process to the character of the material. The lost wax process dates back to the 3rd millennium BCE and changed relatively little over very long periods. That long continuity suggests that the method was already highly effective early on. When a technique survives with only modest adjustment across centuries, it usually means it balances reliability, detail, and practicality very well. The wax model, mold, and poured metal together form a sequence that remains deeply logical. Some ancient crafts found their mature form surprisingly early. Ancient Egypt used flax extensively, while cotton and silk became major textile materials elsewhere. This difference reflects how strongly fiber traditions depended on environment and local practice. Flax processing, spinning, and weaving formed a specific technical world in Egypt, distinct from the cotton-centered traditions of some other places or the silk traditions of East Asia. Textile history is never just about cloth. It is also about the different plants, animals, and working methods that shape each civilization's materials. Purple dye technology reveals how prestige textiles could depend on extremely specialized raw materials. A garment's value might come not only from fine weaving, but from the rare and difficult substances required to color it. This added another layer of labor and exclusivity to the textile. The cloth became precious because its making drew on technical knowledge that was not easy to imitate. Ancient luxury often rested on hard-to-access processes hidden behind a finished surface. Glass beads, faience jewelry, and woven cloth show that adornment technologies often developed alongside ordinary household crafts. A society that learns to spin fibers, shape clay-like materials, or work glass can apply those skills both to daily necessity and to beauty. There is no sharp boundary here. The same technical culture that makes containers or garments may also produce ornaments and elegant objects. Ancient craft traditions often grew by branching outward from practical skill into decoration. Textile production required standardized steps such as spinning, tensioning, passing, beating, dyeing, and finishing. That chain of actions shows how much order lies behind even a simple piece of cloth. A finished textile may feel soft and natural, but it is actually the outcome of repeated controlled operations. Each step affects the next, and mistakes early in the process can shape the final result. Ancient crafts often depended on quiet discipline more than dramatic invention. Ancient cloth was also a kind of data technology, because knots, patterns, and quality could encode status, region, or function. A textile could communicate information without using alphabetic writing. The weave, color, material, and arrangement might tell people something about identity, role, or place. This reminds us that information can be stored in form, not only in words. Ancient societies were often very skilled at reading meaning in material details. Quippers used cords and knots as an accounting apparatus in the Andes. This makes them one of the most fascinating alternatives to familiar writing systems. Instead of marks on a flat surface, they stored information in a hanging structure of fibers. Quantity and perhaps other categories could be represented through knot type, placement, and cord arrangement. It is a powerful example of how human beings can build information systems out of very different kinds of material logic. A quipu consisted of a primary cord with pendant cords and sometimes subsidiary cords attached beneath them. This layered structure gave the device internal organization. Information could be grouped, subdivided, and related through the physical arrangement of cords. The system is not random at all. Its form suggests hierarchy, sequence, and ordered connection in a way that can be handled by the hands, as well as understood by the mind. Quippers demonstrate that information technology in the ancient world did not always require ink or script. Knowledge could be held in knots, fibers, tension, color, and arrangement. This broadens our sense of what a record can be. Ancient societies did not all solve the problem of memory in the same visual way. Some built their records from thread rather than marks. Textile-based information systems show that soft materials could carry administrative meaning just as hard tablets did. We often imagine durable information as something carved, baked, or written on rigid surfaces. But a carefully structured cord system could also preserve and organize important data. This is a helpful reminder that softness does not mean simplicity. Ancient technology sometimes placed authority and memory in flexible things. Ancient crafts often blurred the line between practical goods, luxury goods, and record-keeping tools. A woven object might clothe the body, signal status, and store information all at once. A glazed item might be decorative, symbolic, and durable for daily use. Ancient technologies were rarely trapped in one category. Their meanings and functions often overlapped in calm and interesting ways. The Indus civilization is famous for urban planning that included baths, drains, and organized street layouts. This tells us that city design there was not accidental or purely ornamental. Infrastructure was built into the pattern of settlement itself. Streets, water, and sanitation were thought about together, not one by one after the city already existed. Ancient urban sophistication often begins with such planning. Mohenjo-daro's sewage and drainage systems show that waste management was already a municipal technology in the Bronze Age. This is easy to overlook because drains are less dramatic than palaces or temples. Yet their presence reveals a great deal about daily life and organized civic effort. A society that manages waste effectively is solving a quiet but essential problem. Ancient urban success often depended on exactly these unseen achievements. Covered drains and inspection points in Indus sanitation systems indicate planned maintenance rather than one-time construction. This is a very important detail. It means the builders expected the system to need checking, cleaning, and repair over time. In other words, they were designing not only for use, but for upkeep. Long-lasting technology usually depends on that kind of foresight. The Great Bath at Mohenjo-daro is usually linked to ritual bathing rather than ordinary domestic use. That distinction matters because it shows water architecture serving not only hygiene, but also shared ceremonial or symbolic practice. A large, carefully made bathing structure suggests collective importance. Ancient technology often crossed into ritual life, giving practical materials and spaces deeper meaning. Water could cleanse physically and signify more than that. Indus cities used baked brick on a large scale, which points to standardized production and building conventions. Brick-making at that level requires repeated dimensions, controlled firing, and broad coordination. Standardization is itself a kind of quiet technology, because it allows structures to be built more efficiently and predictably. When many people use the same material format, whole cities can take shape with greater coherence. Ancient urban order often depended on this unseen regularity. Indus houses often had upper stories or accessible roofs, showing that domestic architecture was more elaborate than simple ground-level shelters. This suggests a richer and more layered urban life than older, simplified images of the Bronze Age might imply. Homes were being designed with vertical use in mind, which changes circulation, privacy, and daily activity. Ancient domestic space could be thoughtfully organized, not merely functional in the narrowest sense. The Indus civilization represents a strong example of fitting human settlement to a particular environmental setting. Cities and towns were not placed randomly, but shaped in relation to water, terrain, and practical needs. This is one of the calmest lessons in ancient technology. Success often comes from adaptation rather than domination. A settlement lasts when it understands where it is. Environmental fit can be as important as engineering skill itself. Indus craft technology included technically impressive copper and bronze casting by the lost wax method. This shows that urban planning and fine craft skill were developing side by side. The same civilization that organized drains and streets also mastered delicate metal shaping. Ancient technological sophistication rarely belonged to only one field. Different domains of skill often rose together within the same cultural world. The presence of many towns and villages in addition to large cities suggests that Indus technological systems were region-wide rather than isolated urban exceptions. This means the knowledge and practices that supported sanitation, craft, and building were distributed across a broader social landscape. A civilization is not advanced only because one city is impressive. It is advanced when many connected places share working systems. The Indus world appears to have had that wider technological reach. Ancient urban technology often becomes most visible in its plumbing, drainage, and standardization rather than in dramatic monuments. This is a gentle thought to end on, because it changes where our attention goes. The greatness of a civilization is not only in what rises highest above the ground. It is also in what quietly works beneath daily life, carrying water, removing waste, and keeping routine possible. Some of the most important ancient achievements were designed not to be admired, but simply to function well. Mesoamerican civilizations built calendrical systems that linked astronomy, ritual, and historical recording. This made timekeeping much more than a way to count passing days. The calendar helped people place ceremonies, agricultural cycles, royal events, and cosmic observations into one connected framework. In that sense, time was being organized as both a practical tool and a cultural pattern. Ancient calendars often served as bridges between the sky above and the human world below. Chinampas transformed shallow lake environments into highly productive agricultural zones. Instead of avoiding wet landscapes, people learned how to work with them and turn them into fertile growing systems. By building long raised plots and managing surrounding water, they created places where crops could thrive with unusual intensity. This shows a very calm and confident form of environmental engineering. Ancient farmers were not always limited by difficult terrain. Sometimes they reshaped it into an advantage. The Chinampa system shows that ancient people sometimes engineered ecosystems instead of merely using them as they found them. That is one of the most interesting things about it. The goal was not just to plant seeds in available soil, but to build a new agricultural setting that could support sustained production. Water, mud, plants, and human labor were combined into a stable growing landscape. It is a reminder that ancient technology often involved changing relationships between land and life, not just adding tools. Maya inscriptions were once thought to be mostly religious, but much of the deciphered content turned out to be secular and historical as well. This matters because it changed the way scholars understand Maya writing and knowledge. The inscriptions were not only about sacred symbolism. They also recorded events, rulers, dates, and other matters tied to lived history. Ancient writing systems often reveal more variety once they are better understood. Ancient American textile traditions were advanced enough to stand beside those of the Old World on technical grounds. This is important because it reminds us that high-level craft expertise developed independently in many parts of the world. Fine weaving, dyeing, and fabric design did not belong to a single civilizational center. Across the Americas, people learned how to work fibers with precision, patience, and artistic control. Ancient textile mastery was truly global. Quippus allowed Andean administrators to manage information through fiber structure and not arrangement. This means that administration did not always rely on ink, carved symbols, or flat writing surfaces. Instead, information could be organized through chords, positions, and tactile structure. That required training and agreed methods of interpretation, just like any other record system. It is one of the clearest examples of ancient information technology taking a form very different from what many people expect. The Americas show that complex technologies such as accounting, weaving, and water management evolved independently outside Eurasia. This is a valuable lesson because it broadens the picture of ancient innovation. Human ingenuity did not follow one single path from one single center. Different societies, facing different environments and needs, created their own powerful solutions. Technological complexity is a recurring human pattern, not the property of one region alone. Ancient technology should not be judged only by metal weapons or large stone monuments, because sanitation and record systems were equally important. It is easy to focus on objects that look dramatic or imposing. But many of the most transformative ancient systems were quieter, such as drainage, water control, and ways of storing information. These shaped everyday life, health, and administration in profound ways. Civilization often depends most on what works steadily in the background. Mesoamerican and Andean examples remind us that ancient technology includes ecological design and administrative method as much as machinery. A society may show great technical skill through landscape management, accounting systems, textile complexity, or calendrical precision without needing machines that resemble later industrial devices. This wider view helps us appreciate ancient achievement more fairly. Technology is not only about moving parts, it is also about organized systems that solve real problems across time. Across the ancient world, urban success usually depended on unseen systems for water, food, counting, and maintenance. Cities could only thrive when daily needs were met in stable and repeatable ways. That meant channels had to flow, Stores had to be tracked, crops had to arrive, and repairs had to happen. Monumental buildings may tell one story, but infrastructure tells another. Ancient urban life rested on quiet systems of reliability. China developed iron casting at a remarkably early date, compared with many other parts of the world. This gave Chinese metalworking a distinctive path, because casting iron allows for different kinds of production than techniques focused only on forging. Once a society learns how to handle molten iron effectively, it can produce tools and components with new consistency and scale. Early mastery of this process had wide consequences. Metallurgy can reshape agriculture, craft, and daily life all at once. Ancient China also became an early center for paper, porcelain, brass, and Castilian agricultural tools. This breadth is especially striking. It shows that technological leadership can span very different domains at the same time, from writing materials to ceramics to farming equipment. A civilization does not advance only in one direction. Sometimes many fields of skill grow together, reinforcing one another in a larger pattern of innovation. The significance of Keelan's papermaking process lay not only in invention, but in lowering cost and improving practicality. A writing material becomes historically transformative when it is not just possible, but usable at scale. If a surface is too expensive or too inconvenient, its broader cultural effects remain limited. Paper changed this by making recorded information lighter, cheaper, and more accessible. Sometimes the real breakthrough is not the first appearance of a material, but its improvement into widespread usefulness. Paper's success came partly from solving the problems of earlier Chinese writing surfaces, such as bamboo slips and expensive silk. Bamboo could be heavy and awkward in large quantities, while silk was valuable and not ideal for everyday administrative use. Paper offered a softer, lighter, and more economical alternative. This made writing, copying, and storing information more manageable. A better surface can change how widely knowledge circulates. The spread of paper from China to Central Asia, then to Baghdad, and later into Europe, is one of the clearest examples of a material technology reshaping communication across continents. As paper moved, it did more than replace older surfaces. It changed the economics of writing, copying, record-keeping, and education. A technology that reduces the burden of storing information can transform whole intellectual worlds. Paper's journey is therefore also a journey in the expansion of cultural memory. Zhang Heng's seismoscope did not record a full earthquake waveform, but it could indicate that distant shaking had occurred. That may sound limited by modern standards, yet it was a remarkable step. The device turned an unseen event into a physical sign that people could observe and interpret. Detection is often the first stage in scientific instrumentation. Before measuring everything in detail, a society may first need a reliable way to know that something has happened at all. The seismoscope's design, with dragons and frogs indicating direction, shows that ancient instruments could combine symbolism with function. The visual form was not merely decorative. It helped make the result understandable and memorable. Ancient devices were sometimes designed to communicate information in ways that were both practical and culturally expressive. Science and symbolism were not always separated into different worlds. A device that merely detects an event can still be technologically revolutionary, even if it does not measure every aspect of that event. This is a calming and useful point to remember. Knowledge often advances in stages. First, something becomes detectable, then describable, then measurable in finer detail. The seismoscope belongs to that first important stage, where hidden events are made visible enough to enter human awareness. Crossbows used a short barrel fixed transversely on a stock with a groove, sear, and trigger. That arrangement gave the weapon a very different mechanical logic from a hand-drawn bow. The user could hold stored energy in the system until the moment of release, rather than depending on continuous muscular tension. This introduced more control over timing and aiming. Ancient weapon technology often advanced through mechanisms that separated force storage from force release. The crossbow is a reminder that trigger mechanisms were significant ancient achievements in controlled release. A trigger may seem like a small thing, but it allows stored energy to be held safely and then released precisely when intended. This principle appears in many technologies, not just weapons. It is one of the deep ideas in mechanics. Ancient inventors understood that control over release can matter just as much as raw power. Wheelbarrows were invented in China and gave a single-person leverage over loads that otherwise might require multiple carriers. That is a very practical transformation of labor. By placing weight in relation to a wheel and handles, the device let one person move heavy material with greater efficiency. Ancient transport technology was often about reducing strain as much as increasing speed. A simple shift in balance could change how work was done every day. Coal was already being used as a fuel in China during the Six Dynasties period. This shows that ancient energy history was more varied than many people assume. Wood and charcoal were important, but they were not the only fuels people learned to exploit. The use of coal reflects both practical need and knowledge of local resources. Fuel choices can reshape industries, heating, and metallurgical possibilities across a society. The Chinese chain pump shows how hydronic technology benefited from advances in casting and metal availability. A machine often becomes more useful when better materials make its moving parts more durable and more widely producible. This means hydraulic progress was not isolated from metallurgical progress. Technologies support one another in quiet ways. Better metal can improve water lifting, and better water lifting can support agriculture and settlement. Porcelain became one of China's most admired technological exports to the wider world. Its reputation came from a combination of strength, fineness, translucence, and beauty. Porcelain did not merely serve as a container material. It became a symbol of sophisticated firing control and ceramic mastery. Ancient and early historic technologies often gained global fame when they brought together technical difficulty and unmistakable visual distinction. The magnetic compass, papermaking, silk working, and porcelain are all examples of technologies that later spread from China to other regions. This pattern highlights how one civilization can become a major source of transferable techniques and materials. Some technologies spread because they are easy to imitate. Others spread more slowly because they require deep expertise. But in either case, the movement of useful ideas is one of the great themes of technological history. Ancient Chinese technology often combined practical utility with large-scale cultural transmission. A material like paper or silk was not important only where it began. Once it moved outward, it influenced administration, trade, craft, and habit across distant societies. In that sense, a local innovation could become a civilizational force far beyond its place of origin. Technology often becomes most important when it travels. The breadth of Chinese innovation shows that ancient technological leadership could span writing materials, agriculture, fuels, ceramics, and instruments all at once. This breadth matters because it warns us against reducing ancient civilizations to one signature invention. A truly advanced technical culture often develops multiple strengths that interact with one another. Better materials improve tools, better tools improve farming, and better writing surfaces improve administration. Ancient innovation was often a web, not a single line. Early paper technology mattered because cheap information storage can change nearly every other administrative and intellectual system around it. When writing becomes easier to produce and preserve, Governments can keep more records, scholars can copy more texts, and ideas can circulate more widely. Information has a material cost, and reducing that cost can be transformative. Paper was therefore not just another surface. It was a quiet accelerant of complexity. China's ancient achievements illustrate how materials, science, and information technology can grow together. Better ceramics, better metalworking, better paper, and better instruments all emerge from close attention to substances and processes. When a civilization learns how to manipulate matter more effectively, it often also improves the ways it stores and transmits knowledge. These two domains are linked more deeply than they first appear. Ancient progress often moved through both at once. Alexandrian engineers such as Ctesibius and Hero invented many mechanical contrivances, including pumps and automata. This tells us that ancient engineering was not limited to building roads or warfare. Some inventors worked on compact devices that explored motion, pressure, and sequence in highly refined ways. Their creations show a fascination with what mechanisms themselves could do. Ancient technology included curiosity-driven design, as well as large public works. Ancient automata show that engineering in antiquity included entertainment and demonstration, not only survival or conflict. Devices that moved by themselves could inspire wonder, display technical skill, and reveal principles of motion to those who watched them. This playful side of engineering is easy to overlook, but it matters. Human beings have long used technology not just to meet needs, but also to create astonishment. The desire to make mechanisms seem alive is very old. Hero and related traditions used compressed air and water power in devices that could surprise viewers and demonstrate mechanical principles. This is especially interesting because it shows ancient experimentation with forces that are not immediately visible. Air pressure and flowing water could be harnessed to produce motion, sound, or automatic action. Such devices often stood at the border between spectacle and science. They delighted people while also revealing something about how nature could be guided. The Eolipile is often regarded as the first successful steam turbine, even though it was not developed into an industrial power source. That makes it a fascinating example of a technology that appeared long before the conditions existed for its large-scale practical use. It demonstrated a principle, showing that steam could produce rotation. Yet without the broader material and economic systems needed for industrial application, it remained more of a marvel than a revolution. Ancient technology sometimes discovered ideas earlier than history was ready to fully use them. Pumps in the Hellenistic world revealed that ancient engineers could manipulate fluids with considerable ingenuity. Moving water where it would not naturally go requires understanding pressure, containment, flow, and mechanical action. Such devices show that ancient engineering included subtle control, not only large visible structures. A pump can be small compared with an aqueduct, but it reflects equally serious thought. Ancient technical intelligence often appears in compact forms. Mechanical toys and temple devices show that ancient technology often served social theater and ritual wonder. A moving figure or automatically operating mechanism could create emotional impact far beyond its size. In religious or public spaces, such devices could shape how people felt about the place and what they believed was happening within it. Technology, performance, and symbolism could work together in very deliberate ways. Ancient mechanisms were sometimes designed to persuade the senses as much as to do work. Ancient screw-cutting machines demonstrate that precise rotary motion was understood in more than one context. This matters because cutting or shaping screw forms requires controlled repetition and geometric awareness. It is not merely a matter of rough turning. Precision mechanisms depend on the ability to reproduce a spiral form that behaves predictably. Ancient engineers were already exploring these refined relationships long before modern machine shops existed. The screw press and the Archimedes screw used the same geometric idea for very different tasks: pressing and lifting. This is one of the loveliest examples of a single concept branching into multiple technologies. A spiral form can translate rotation into force in different ways depending on how it is arranged. In one case, it drives downward pressure, and in another, it helps move water upward. Ancient mechanics often advanced by discovering how one idea could serve many purposes. Greek and Roman engineering frequently turned abstract geometry into working devices. Lines, circles, levers, and spirals were not only matters for thought. They were turned into bridges, presses, screws, gears, and instruments. This connection between mathematical form and practical mechanism is one of the deepest themes in ancient engineering. A shape on the page could become a force in the world. The Antikythera mechanism proves that complex gear trains were already possible in the ancient Mediterranean. It shows that ancient craftsmen could produce interacting toothed wheels arranged for highly specific functions. This is not simple carpentry or rough metalwork. It is precise mechanical design. The mechanism stands as a rare surviving witness to a level of sophistication that may once have been more widespread than the surviving evidence suggests. Ancient mechanical sophistication did not always scale into mass industry, but it still reached impressive levels in specialized devices. This is an important distinction. A civilization may know how to build something ingenious without reorganizing its entire economy around it. Specialized devices can be technically brilliant, even if they remain rare. Ancient technology often flourished in that form, concentrated in instruments, luxury mechanisms, or limited applications. Roman bath complexes reveal system integration on a grand scale, while Hellenistic devices reveal refinement on a compact scale. Together, they show two very different faces of ancient engineering. One works through infrastructure, architecture, and urban coordination. The other works through gears, pressure, and small mechanisms. Both are genuine expressions of technical power. Ancient engineering was broad enough to excel in both the massive and the miniature. Ancient engineering could be both playful and practical, often blurring those categories. A mechanism that delights also teaches. A device built for spectacle may reveal principles that later serve more practical ends. Likewise, a practical technology can still carry beauty and drama in its design. The ancient world did not always divide utility from wonder as sharply as modern people sometimes do. Devices such as odometers and seismoscopes show that measurement and signaling were important ancient technological goals. The aim was not only to move things or build structures, but also to know more reliably when something had happened and how much had occurred. A distance traveled, an earthquake detected, a cycle counted. These are all forms of making the world more legible. Ancient technology often served understanding as well as action. Mechanical thinking in antiquity often meant converting one type of motion into another in a controlled and repeatable way. A rotating wheel might count distance, a flowing liquid might mark time, a trigger might release stored force, and a spiral might lift water. These conversions are the heart of mechanism. Ancient engineers were skilled at noticing how one movement could be translated into another useful one. Much of mechanics begins in that quiet insight. Ancient inventors frequently excelled at elegant mechanisms even where available power sources remained limited. Without engines in the modern sense, they still found ways to create precision, rhythm, and transformation through hand power, flowing water, gravity, compressed air, and heat. Limited power did not mean limited imagination. It often encouraged more ingenious use of the forces that were available. Ancient mechanics is full of that kind of elegance. The technical achievements of Greece and Rome include hydraulic, pneumatic, and rotational devices, as well as architecture. This matters because it broadens the story beyond monuments and roads. Ancient engineering was not only static and structural. It also explored movement, pressure, circulation, and repeated action. The world of mechanisms was already active beside the world of buildings. Precision in antiquity often came from craftsmanship and geometry rather than from high-energy machinery. A skilled hand, guided by careful proportion, could achieve surprising exactness. That is one reason surviving ancient mechanisms feels so impressive. They were made without the industrial tools later ages take for granted. The precision came from knowledge, patience, and disciplined making. Ancient machines were often built to embody principles visibly, which is one reason they remain so intellectually striking. When we look at a screw, a gear train, a sundial, or a water-raising wheel, we can often see the core idea working in front of us. The machine becomes a physical explanation. Ancient technology sometimes teaches through its form as much as through its function. That visible clarity is part of its enduring charm. The surviving record of ancient mechanics is fragmentary, which makes every well-preserved device disproportionately informative. A single object like the Antikythera mechanism can illuminate an entire lost world of skill, because so few comparable items remain. This creates a quiet sense of both wonder and caution. We know enough to be impressed, but not enough to assume we see the full picture. Ancient technology may have been richer than the surviving evidence allows us to measure. Ancient mechanical sophistication did not always grow into mass industry. It had still reached extraordinary levels in specialized devices. That is a gentle reminder that technical brilliance does not always appear as a vast economic transformation. Sometimes it appears in a single instrument, a finely made mechanism, or a beautifully solved problem. A civilization may understand a principle deeply, even if it does not build an entire industrial world around it. Ancient technology often shines this way, through concentrated excellence rather than endless scale. Roman bath complexes reveal system integration on a grand scale, while Hellenistic devices reveal refinement on a compact scale. One approach gathered water, heat, architecture, and public life into immense civic spaces. The other explored gears, pressure, valves, and motion inside smaller instruments and mechanisms. Together, they showed two calm faces of ancient engineering, the monumental and the miniature. Both required planning, skill, and a deep respect for how parts work together. Ancient engineering could be both playful and practical, and those two sides often blended naturally. A mechanism might entertain, surprise, or inspire wonder, while also teaching a principle of motion or control. A useful device might still be elegant and memorable in its design. This makes the ancient world feel especially human, because people did not always separate utility from delight. They often wanted their tools and systems to work well and to feel impressive at the same time. Devices such as odometers and seismoscopes show that measurement and signaling were important ancient technological goals. It was not enough simply to travel or to experience an earthquake. People also wanted a way to register what had happened in a more stable, visible form. The machine became a translator between the event and human awareness. Ancient technology often moved toward this quiet ambition, making the world easier to notice, count, and understand. Mechanical thinking in antiquity often meant converting one type of motion into another in a controlled and repeatable way. A rotating wheel might become a count of distance. A flow of water might become a measure of time. A hidden force might become a visible signal or a useful lift. This way of thinking is one of the oldest roots of machinery. Ancient inventors were often at their best when they found a calm, reliable way to turn one movement into a different kind of result. Ancient inventors frequently excelled at elegant mechanisms, even though available power sources were limited. Without engines in the modern sense, they still used gravity, hand force, flowing water, compressed air, and heat with remarkable creativity. This limitation did not make their work simple. In many cases, it made it more subtle. When power is scarce, design has to become sharper, and ancient mechanisms often show exactly that kind of disciplined cleverness. The technical achievements of Greece and Rome include hydraulic, pneumatic, and rotational devices, as well as architecture. This is important because it broadens the picture beyond arches, roads, and stone monuments. Ancient engineering also explored water pressure, moving air, turning motion, and repeated cycles of action. The world of antiquity was not only a world of structures, it was also a world of mechanisms, fluid control, and carefully guided motion. Precision in antiquity often came from craftsmanship and geometry rather than from high-energy machinery. A skilled artisan, guided by measurement and repetition, could achieve results that still feel surprisingly exact. This is one reason ancient devices continue to command respect. Their makers worked without modern industrial tools, yet still reached high levels of reliability and finish. Precision can come from patient intelligence as much as from powerful equipment. Ancient machines were often built so that their principles could be seen almost directly in their form. A screw shows its spiral logic. A sundial shows time through shadow. A water-raising wheel shows its sequence of lift and release. This visible clarity is part of why ancient mechanisms still feel satisfying to think about. They do not hide their working idea entirely. The machine itself becomes a quiet explanation. The surviving record of ancient mechanics is fragmentary, which makes every well-preserved device especially meaningful. A single instrument can illuminate a lost world of skills because so little has endured by accident of time. That adds a certain softness to the study of ancient technology. We know enough to admire it, but not enough to assume we have the whole picture. What survives is like a small window into a much larger workshop that has mostly disappeared. Desert civilizations often specialized in water-saving technologies because moving and preserving water mattered more than sheer abundance. In such places, every drop carried weight. A clever channel, reservoir, or underground passage could matter more than a dramatic machine. This gave rise to forms of engineering shaped by patience, protection, and careful distribution. Ancient desert technology teaches that some of the greatest achievements are designed not for excess, but for wise economy. Qanad settlement patterns in Iran are closely related to the distribution of alluvial fans and groundwater access. This means settlements did not arise randomly. They grew where underground water could be reached and guided through carefully planned channels. Technology and geography worked together in a very direct way. Ancient communities often formed where the land offered not only shelter and soil, but also a hidden path for water. Underground water channels had the advantage of reducing evaporation in hot climates. This is a beautifully quiet solution to a serious problem. Instead of fighting the heat directly, ancient engineers placed the water where the sun could not easily take it away. The method depends more on restraint and concealment than on force. Sometimes ancient technology succeeded by protecting a resource rather than by multiplying it. The engineering of levers in Gaziantep required keeping tunnel slope exact enough for constant flow over long distances. That kind of work demands patience and careful judgment. If the slope is too steep, water may rush destructively. If it is too slight, the flow may stall. Ancient hydraulic success often depended on this kind of balance, where a very small error could matter greatly over time. A gentle gradient became an instrument of survival. Petra's water management included channels, diversions, and protective carving to handle both scarcity and sudden runoff. This dual purpose is what makes the system so impressive. In an arid landscape, water is precious when rare and dangerous when it arrives violently. The same society had to build for shortage and for flood. That kind of engineering reflects not only skill, but a deep attentiveness to the moods of the land. Ancient oases in northern Arabia paired irrigation with massive enclosing walls, linking hydraulic technology with protection and settlement. Water and security were not separate concerns. A place that could support life in the desert was also something worth defending and organizing carefully. This means engineering often extended beyond channels and storage into the broader shape of habitation. Ancient technology could bind together food, safety, and place in a single design. UNESCO describes these walled oases as using innovative technical solutions that helped sustain longevity over millennia. That long endurance matters because it shows the systems were not merely clever in theory. They worked well enough to support repeated life across generations. The best ancient technologies often proved themselves not through novelty, but through lasting usefulness. A system that can be maintained and relied upon for centuries carries its own quiet authority. Ancient Saudi hydronic works included not just dams, but also designed water outlets and stepped facades with preserved plaster. These details show that practical water systems were carefully finished and thoughtfully organized. The builders were not only trying to hold water back, they were shaping how it moved, where it emerged, and how surrounding surfaces resisted wear. Ancient engineering was often richer in detail than a distant glance would suggest. Water transport technologies in deserts often generated distinctive architecture such as reservoirs, gardens, mills, and underground networks. Once water is moved successfully, it changes everything around it. New forms of building and cultivation become possible. A hidden camel may eventually shape visible life above it in the form of greenery, storage spaces, and settled communities. Ancient hydraulic technology often left a strong architectural afterlife. In arid regions, the line between civil engineering and everyday survival was especially thin. A channel was not an abstract improvement. A dam was not merely a prestige project. These things often determined whether a settlement could continue at all. That gives desert engineering a calm seriousness. It reminds us that ancient technologies were often responses to basic realities, built with the understanding that life itself depended on their success. Ancient technology was rarely isolated from religion, because many materials and devices also carried symbolic or ritual meaning. A useful object could also be a sacred one. A practical plant could appear in ceremonial form. A building for bathing could carry social and spiritual importance as well as bodily function. In the ancient world, the technical and the symbolic were often woven together, quietly sharing the same materials and spaces. The same papyrus plant that served daily practical needs also appeared in protective amulet form in Egypt. This is a lovely example of a material moving from ordinary use into symbolic life. A plant that became rope, mats, and writing surfaces could also become an image of protection and flourishing. Ancient societies often allowed useful things to gather layers of meaning over time. Technology and symbolism could grow from the same root. Faience was technically made from common ingredients, yet it was socially valued alongside precious stones and metals. That contrast is part of its charm. It shows that ancient people recognized beauty and significance, not only in what was naturally rare, but also in what skilled transformation could produce. Heat, minerals, and controlled process could elevate ordinary substances into something deeply admired. Value often came from knowledge as much as from scarcity. Public baths could be places of hygiene, social life, imperial display, and technological demonstration all at once. They brought together water management, architecture, heating systems, and public habit in one shared setting. A person entering such a bath entered both a social world and an engineered environment. This is one reason Roman baths remain so evocative. They show how ancient technology could shape daily life gently, surrounding people with organized comfort. Ancient books changed shape according to material constraints, from clay tablets to papyrus rolls, and later to other forms. The way knowledge is stored always depends partly on the nature of the material carrying it. Clay invites one kind of format. Papyrus invites another. The physical form of a text affects how it is handled, copied, moved, and preserved. Ancient information technology was never separate from the bodies of the materials themselves. The spread of paper from China is one of history's clearest examples of how a material innovation can reshape communication across continents. A lighter, cheaper writing surface does more than replace an older one. It alters administration, scholarship, copying, storage, and education. Over time, it changes how easily ideas can travel and endure. Some technologies are powerful not because they look dramatic, but because they quietly reduce the cost of thought. Some ancient technologies lasted because they were simple, while others lasted because they were scalable. The shaduf is a good example of the first kind, and aqueducts of the second. A shaduf survives because it is easy to understand, make, and repair. An aqueduct endures because it can support large populations and broad civic life. Ancient success could take more than one form. What mattered was not complexity alone, but fitness for purpose. Ancient engineers often solved problems through geometry and gravity before they could solve them through concentrated power. This is one of the most peaceful lessons in the whole subject. Instead of overwhelming nature, they often worked with angle, slope, balance, and shape. A well-chosen form could accomplish what brute energy could not. Ancient technology frequently succeeded by listening carefully to how the world already behaves. Many ancient inventions remained in use for centuries because they matched human needs and local materials with unusual efficiency. A tool endures when it fits the hand, the landscape, and the task all at once. The most lasting technologies are often not the most dramatic. They are the ones that become quietly natural within daily life. Ancient systems often survived because they were practical in the deepest sense. They belonged where they were used. A great deal of ancient technological brilliance lies in maintenance-friendly design, not only in invention itself. A system that cannot be repaired easily may fail, no matter how clever it seems at first. Ancient builders often understood this well. They created shafts for access, standard forms for replacement, and structures that local communities could keep alive over time. Endurance often depends less on novelty and on the ability to care for what already exists. Ancient technologies often appear simple only because their complexity is distributed across materials, habits, and skilled labor, rather than concentrated in one obvious machine. A loom, a canal, or a writing system may seem straightforward until one notices how many decisions and repeated practices hold it together. The intelligence is spread out across the whole process. This is part of what makes ancient technology so easy to underestimate. Its subtlety often lives in routine. Clay tablets, quippers, and paper all solved the broad problem of storing information, but each did so through a completely different material logic. Clay preserves through hardness and durability. Quippers organize through cords and knots. Paper spread through lightness, flexibility, and low cost. The mead is the same, yet the chosen solution changes everything about how information is handled. Ancient information history is really a history of different materials learning to remember. Aqueducts, qanats, and chimampas each show a different ancient strategy for managing water, transport, tapping, and landscape creation. An aqueduct brings water from afar. A qanat accesses hidden groundwater and guides it gently forward. A chinampa reshapes a watery environment into fertile land. These are wonderfully different answers to a shared necessity. Ancient technology did not solve one central problem in one standard way. It solved it through many local forms of imagination. Lost wax casting and glass blowing reveal that ancient artisans could work with both molten metal and molten silica at high precision. These are very different materials, each with its own heat behavior and demands. Yet both could be guided into fine form by people who understood timing, temperature, and shaping. Ancient craft often reached its highest beauty when materials were most fluid and difficult. The maker had to intervene at exactly the right moment. Roman concrete and Egyptian faials both depended on controlled chemistry long before chemistry existed as a formal modern science. Ancient people may not have used modern terms, but they knew by experience how ingredients reacted, how heat transformed mixtures, and how the final material would behave. Their knowledge was practical, repeatable, and often highly refined. This reminds us that scientific understanding can live in craft long before it becomes abstract theory. The strongest ancient technologies were often systems technologies, such as sanitation networks, rather than isolated tools. A drain, a channel, a storage method, or a street plan may not look as striking as a fine weapon or a decorative object. Yet such systems quietly support whole populations. Ancient civilization often depended most on what worked continuously in the background. The largest effect sometimes came from the least theatrical devices. Measuring time, measuring distance, and detecting earthquakes all show that ancient innovation was partly about making invisible processes legible. Time passes whether or not it is counted. A road extends whether or not distance is marked. An earthquake may occur far away before anyone nearby understands it. Ancient devices help turn these elusive realities into something visible, countable, or signal-like. Technology often begins when experience becomes readable. Ancient textile and dye technologies remind us that softness and color were as technologically significant as stone and bronze. It is easy to think first of hard materials when imagining the ancient world. Yet some of the most sophisticated work involved fibers, tension, pattern, pigment, and subtle treatment of surfaces. Cloth and dye carried knowledge, labor, and status just as surely as masonry and metal did. Ancient technology also lived in what touched the skin. Information technology in the ancient world included scripts, numerals, chords, tables, and calendars, rather than any single medium. That variety is worth resting with for a moment. Human beings have always looked for ways to hold thought outside the mind, but they have done so through many materials and structures. A number sign, a knot, a tablet, a water clock, and a calendar all belong to that wider story. Ancient information was stored in many shapes. Ancient urban technology can often be judged by how quietly it handled waste and water, rather than by how loudly it displayed wealth. This is a calm but powerful standard. A city may impress the eye with monuments, but daily life depends on whether water arrives where it is needed and waste leaves where it should. The most humane engineering often disappears into ordinary function. Ancient cities were strongest when their hidden systems were dependable. Ancient technology frequently spread through trade and imitation, but local environments still shaped final designs. A useful idea might travel far, yet it would rarely remain unchanged. Materials, climate, terrain, and local habits all influenced how the borrowed technology was rebuilt. This is why ancient inventions often appear as families of related forms rather than exact copies. Shared ideas still had to make peace with place. A device can be ancient and still feel modern in principle, as seen with screws, pumps, odometers, and paper. The materials and surrounding systems may differ, yet the core logic remains familiar. That is one reason ancient technologies continue to feel close to us. They do not belong to a completely alien world. Many of their ideas still move quietly within the tools and systems of everyday life. Some ancient innovations were prestigious luxuries, while others were quiet background systems, and both could transform civilization. A brilliant dyed textile and a reliable drainage network belong to very different parts of society, yet each reveals something important about technical culture. One may shape prestige and exchange, the other health and daily function. Ancient technology was never only about necessity or only about splendor. It lived in both realms at once. Technologies tied to counting and scheduling often had effects far beyond their material size, because administration depends on regular records. A small tablet, a notation system, or a calendar may seem modest compared with a dam or aqueduct. Yet such devices can organize taxes, rituals, storage, labor, and memory across whole communities. Tiny information tools often support very large structures of life. Ancient order frequently rested on compact forms of notation. Ancient engineering success often came from understanding limits such as slope, weight, tension, evaporation, and material brittleness. This is one of the gentlest lessons in the history of technology. Good builders and makers did not ignore the limits of their materials and landscapes. They studied them, accepted them, and worked with them carefully. Wisdom in ancient engineering often meant knowing how far something could go without failing. In many cases, ancient people preferred repairable and modular solutions because replacing entire systems was too costly or difficult. A channel could be cleared, a section rebuilt, a component remade, a tool edge replaced. This practical habit helps explain why so many older technologies were able to endure. Survival depends on the ability to mend. Ancient design often carried within it an understanding that maintenance is part of life. The survival of Shadufs, Kanats, and Archimedes' screws into later periods shows that elegant low-energy technologies can outlast more dramatic inventions. A powerful machine may dazzle for a time, but a simple and reliable device often remains useful much longer. These ancient systems endured because they matched local realities and human rhythms well. Their strength was not noise or speed, but lasting fitness. Quiet efficiency can be one of the most durable forms of genius. Ancient technologies were often inseparable from labor organization because the machine and the human routine formed one working unit. A loom required practiced motion. A canal required shared maintenance. A press needed coordinated effort. Ancient systems were rarely independent of people in the modern automated sense. They worked because tools, bodies, habits, and timing were all aligned together. The ancient world produced not one technological tradition, but many parallel traditions adapted to rivers, deserts, forests, coasts, and cities. This diversity is one of its most comforting and beautiful truths. Human beings kept meeting different environments with different kinds of skill. No single solution ruled everywhere. Instead, many technical worlds grew side by side, each shaped by place, material, and need. Taken together, ancient technologies show a consistent pattern. People repeatedly turned observation, repetition, and local materials into systems that could endure for centuries. They watched carefully, they practiced patiently, and they built with what the world around them offered. Over time, these quiet efforts became channels, scripts, textiles, mechanisms, cities, and instruments. And as the night grows softer, it is peaceful to remember that so much of human history was shaped not only by force or conquest, but by steady hands, learning how to make useful things last.